food you can eat without teeth. My favorite.
Sometimes I miss Dad's cooking. Sorry, Mum.
Sometimes I do too. I've washed your uniforms for Monday. Excited? How are you feeling, Mol?
It's like you said. There's no changing it. Can I please go now?
Just eat.
I don't feel well.
Cramps?
Gross. No, I want to be alone.
Oh, that's new for you.
Oh, shut up, Till, you moron.
Molly,
What?
don't speak to her like that.
Sorry.
Don't speak to me like that either.
Oh, what, Mum?
Do you have any manners?
Do you even like me? Do you? Do you?
I'm your mother, Molly. I'm not your friend. It doesn't matter if I like you.
Power surge detected.
Hey, is that Henry?
Systems back online.
Hey everyone! Now that you've been diving into Unreal Engine 5 and our brand new sample projects, we have 2 new tech talks to share. First, we dive into exactly what Lyra Starter Game is, why we made it, and how you can use it to get a head start on creating your new cross-platform game in UE5. We cover what's included in the sample and the modular development ethos behind it, then give a quick tour of how a gameplay experience is built in UE5. In our second talk, find out how we're using Common UI to streamline cross-platform development and how we leverage materials to develop performant and good-looking UIs. We'll also discuss some development and performance benefits of using Unreal Engine materials as the foundational UI art asset in UMG and why you might choose them over a more bitmap-heavy implementation method. Watch both of the Lyra Starter Game talks on the Unreal Engine YouTube channel. The April Marketplace sale is upon us, and you can get 50% off on over 1,000 fantastic products. From customizable car configurators and garage props to lush tropical beaches and sci-fi settings, there's something for everyone. Act fast, the sale ends Sunday, April 24th. Head to the UE Marketplace and find your favorites today. From a desire to inspire people to cooperatively play together, Chet Falsek, known for his work on Half-Life 2, Portal, and the Left 4 Dead franchise, founded game studio Stray Bombay Company. Their first title, The Anacrysis, which hosts a team of 4 star-tossed stranded characters fighting to survive their first encounter against aliens on a massive starship, is steeped in a wonderfully kitschy design language and is flush with colorful retro futurism. Head to the Unreal Engine feed where we caught up with the team to learn about the inspiration and evolution of The Anacrysis. While there, discover how South Korean animation studio Locus leveraged the power of real-time technology for Yumi's Cells, a new TV drama based on a popular webtoon that takes us inside a lead character's brain with 3D animations. We connected with the artists behind the TV series to find out how they approached the challenge of representing human thinking in such a unique way. And bouncing over to this week's community spotlights, explore a fascinating imaginative scene from Wang Chen. The character Cody is quite adorable and very well put together, with a lovely environment for them to explore and live in, all rendered in UE5. Head to their ArtStation page to see more and let them know what you think. Retreat to a secluded home in the forest created by Mad Idea X Max. This lovely A-frame house was built in 3ds Max with textures created in Substance Painter before being assembled in Unreal Engine. Venture over to the forums to share your feedback. Once upon a time, princesses were fickle and flighty. Those days are over. Now Upon a Time is a storytelling project that reimagines classic tales with a modern, empowering, and inclusive message. In this new take, Lil Ruby Riding Hood travels from Brooklyn to see her beloved grandmother in suburban Connecticut. Upon arrival, she finds someone she didn't expect, Mr. Howell, a financial advisor more cunning and dangerous than any wolf. But our confident, savvy hero has a trick or two up her hoodie sleeve once the real game ensues. Learn more about the team's work at nowuponatime.org. Thanks for watching this week's News and Community Spotlight.
Hello, everyone, and welcome to Inside Unreal, a weekly show where we learn, explore, and celebrate everything Unreal. I am your host, Tina, and today with me I have two very special guests here from Fluid Simulation to walk through some of the really awesome stuff that I know we've gotten a lot of requests for. So first, let's go ahead and let them introduce themselves. Devin, would you like to tell us a little bit about yourself?
Sure. My name is Devin Penny. I'm a senior physics engineer at Epic. Been working on fluid simulation here for a couple years now, and we're just really excited to get into 5.0. I've worked in simulation for a number of years, worked at DreamWorks for 7 years, and also was in VR doing cinematic experiences there too, and specializing with fluids and volume rendering. So yeah, this has been my passion for many years, and excited to show you guys a lot of stuff today.
Yes, very excited myself as well. Dan, would you like to tell us a little bit about yourself?
Sure. I'm Dan Pearson. I'm a technical product manager, focusing on media and entertainment. I've been with Epic Games for 3 years now, worked on the Niagara team and special projects. And before that, I was at ILM for 18 years, working on Star Wars movies and Star Trek movies and lots of other movies. So I've been effects TD, effects supervisor for a lot of years. And this is a really great opportunity and a great experience turning all this into real time and Unreal in general.
Yeah, it has been absolutely incredible seeing a lot of the stuff that you two have made and created and the stuff that you've walked through before. So I am super excited that we get to walk through some of that ourselves today as well. I don't want to take up too much time talking. I want to get right into the meat of it. So Devin, would you like to start us off?
Sure, absolutely. Okay, oops. Yeah, so what we're going to talk about today is this new plugin that we have in Unreal Engine 5 for fluid simulation. It's something that Dan and I have been working on for a long time now, and we'll just dive right into it. So the plugin is called Niagara Fluids. It's an implementation of 2D and 3D liquids and gases, and has simulators that you can use. You can drop them into a level. You can tweak them in the Niagara editor. It's fully built in Niagara, so everything is open for you to change. Everything's open for you to play with. It's also fully integrated into the engine, so you can expect that you can put a fluid into some map and you can add objects for it to collide with. You can have all kinds of things interacting together really seamlessly. And when we say that it's integrated with Niagara, there's no code hidden in the source tree in the sense that everything is in front of you if you're using Niagara. So part of the goal of doing this fluid simulation package in Niagara is to just improve Niagara in general as a visual effects platform. So we're kind of trying to do things even beyond the fluid simulations that we have and like sort of open up a really nice interface for people to do other types of things. And what we had to create to enable this was a whole bunch of reusable modules. So things that people can reuse that are used in the fluid simulation for other purposes. And we'll show some things later that kind of demonstrate that. And also these data structures for 2-dimensional and 3-dimensional grids that you can use for a whole variety of simulations, from flocking and boids, for things like birds and insects, but also for other types of like fake fluid simulations and everything in between, real simulations and that kind of thing. So we have this platform that's really powerful, and we really want to encourage people to tinker. So when you start to play with Niagara fluids and you get comfortable with using the systems, you can open them up, you can really look at all of the details and start to change things. And when we talk about the engine integration, you can pretty much use a lot of the tools that you have available to you in Unreal to work with the fluids. So here we have a little animation from a capture in the engine of using some directional lights to light the fluids. So this is like a cloud, and we're just manipulating some lights as you would for anything in the engine, except to, lighting on slide. So those are the collisions with scene, which we support different types of collisions that we're going to show really soon. And also, because Niagara as a whole is reusable, and that's something also support too with fluids. You can really just think of these fluid simulations as just a new type of Niagara simulation. There's really nothing else special about it other than it works on grids. Anything you can do in Niagara, there's a good chance you can do it with the Niagara fluids. And who is this for? Well, we're really trying to target anyone who is interested in visual effects. So, for instance, you can imagine R&D engineers go in and write these like really complex simulations, or tweak the ones that we provided in the engine as templates to create something that's very specific for either a game or a cinematic. It's really for anything in between there too. And you can also imagine you have effects developers, people who are taking some system the engineers have created and trying to like really manipulate it and add a lot of like interesting features like new forces to sort of guide the fluid in some way. It could be any number of things, but really try to design the effect that will be used either in game or in a cinematic. And then we also want to empower effects artists to take these systems and make them work in whatever scenario that they're intended for, and be able to iterate as fast as they can. So we're really trying to make people work as quick as they can, and also just have available to them all the tools that they need inside of the engine. So you don't need to be going out of the engine to work in other packages. And something that we're going to show today also, especially Dan later, is the idea that we have a scalable UI for all of these uses and all of the people involved. So we have systems that are more appropriate for cinematics and more appropriate for games, but then also UIs that are more appropriate for R&D engineers and more appropriate for effects artists. Cool. So without further ado, we're going to just jump into the engine, and we're going to just sort of go over some stuff. All right. So
Devin, real quick,
yeah,
I think your stream glitched up a little bit for us. Do you mind restarting that real quick?
sure. Restarting which, the editor? Or?
Just your start stream button. If you could just turn that off and back on again. We'll do the classic IT.
Okay. Hang on.
We had a second there where we were losing you.
Oh no.
Metahuman malfunction.
Hang on a sec here. It's not letting me rejoin it. Saying could not access the specified channel or stream key. Please double check your stream key if that's correct. there may be a problem with connecting with the server. I'm not sure. That's not good.
That's all right. We can get all that figured out. This is the beauty of live.
Yeah, it's something,
So,
huh?
yeah, no worries about that. In the meantime, maybe Dan, did you have a couple things that we could walk through while we figure out how we can get Devin set back up
Yeah.
again?
Well, let's jump into the editor, and we'll go through setting one of these guys up and dropping it into a level, and we'll have a play. So this is the launcher version of Unreal 5.0. To get this guy going, it is in a plugin. So the usual way, if you open up the plugins window, if you type fluids, you'll see it pop up. I already have it activated right now, but you can toggle that guy on. It'll ask you to restart the editor. And then just by right-clicking in the content browser, go to a new Niagara system, and you want to create a new system from a template or behavior example. Hit next. And then immediately you'll see a pretty long list of templates that are available. In this particular window, we've got 2D and 3D gas simulations and also 2D and 3D fluid. And then down at the bottom, we have a couple of examples for a shallow water implementation. All of these will be evolving in future releases, but please, feel free to open these up, have a play with them, see what they can do. A good starting point for these things is this simple particle source version for Grid 3D gas. So I'm just going to select that and hit finish. Just call it something semi-meaningful. And then you should be able to just drag this guy straight into the view. Lift it up a little bit. And then you have a 3D fluid in your level just running away. So to go over what this component is doing, what this Niagara system is doing, you'll see this red box that is defining the bounds of the simulation that's going to simulate. And on the faces of each box, you'll see these smaller boxes. That's a visual indication of the size of the cell within the simulation. They'll give you a sense of the resolution, how much detail you'll be able to capture with this particular sim. So looking at on the system component, we actually have the resolution max axis here. This is controlling how detailed the simulation is going to be, and by extension, how expensive the simulation is going to be. So if I lower this, for example, you'll see that these boxes get bigger. That gives you an indication. And now, of course, my fluid is a lot lower on the resolution. But you can play with that directly in the editor. You can obviously switch off the overlays as well. And now all that we're really seeing is just the renderer itself. Okay. Other options that we've got on the component itself, one of the first things you'll probably want to do is get a scene lighting going. There are 2 directional lights already hooked up for you. And by default, it's going to use lighting, which is coming directly from the Niagara system. So you'll always have some kind of lighting going on. But if you want to start linking it to something in your level, then you can change this source actor here and then hook it up to your directional light. And now you're controlling it with this guy here. So as you move it around, it will actually conform to what's going on in the world. Collisions is another one that's fun to play with. There are lots of ways that you can interact with your fluid sim. Everything from static meshes to physics bodies to geometry collections, landscapes. They're all supported. And we'll be doing more tutorials in the coming weeks on exactly how to set each one up just to make it even easier for you to get started. I'm going to give you a quick demonstration just on using a static mesh as a very useful mode. So I can just create a simple shape. I'll create a cube in this case. I'll just make sure it's somewhere within my fluid. Now you'll notice that nothing is happening right now. And this is deliberate. We want to make sure that if you drop a fluid simulation into a complex level, that it's not going to suddenly start colliding with everything in your map. But to get this cube to interact, the only thing that I need to do is I need to add a tag to it. So I can just add an advanced tag here, just hit the plus, and I need to call it Collider. And as soon as I do that, then you can see that the fluid is now starting to interact with this guy. And as I start messing about with it, then I can start altering the behavior. And it's fun, you know, you can start playing around with it and seeing what this gas is going to do as I start wafting this cube through it. Okay. So you'll notice on the fluid sim itself that we have already exposed here the data interfaces for geometry collections, physics assets, and of course the static mesh itself. For the static mesh, you don't actually have to touch this. You just have to keep adding tags to whatever static mesh it is that you want it to interact with. As far as other things on the component level, right now there are just a limited controls on the component level. We will probably add more things as the requests come in. But for now, we can hop into the Niagara editor. So what you're seeing here is a fairly standard setup across most of these templates. This guy here, this is the main fluid simulator that is doing most of the work. And you'll notice that it's been collapsed down. This is a new feature for 5. It's called the emitter summary. And what that means is that we've promoted up parameters from the emitter into these tabs. So the most common things that you will want to adjust, you can now find in this emitter summary. And this emitter is now collapsed. Now, I can open this guy up. This is a bit of an advanced topic, but you'll see that there are lots of things going on inside this emitter, and it obviously is a little bit daunting for anyone who just wants to start to play with fluids. But once you become comfortable with the main controls, feel free to open that guy up, start digging into it, and see how you get on. So the way that this is working is the main fluid emitter is here. This emitter over here is what is sourcing data into the simulation. I can switch off the fluid sim and switch back on this renderer. And you'll see that here that these are the particles that are actually driving data into the sim. You can do pretty much anything you like with this emitter. The gas is looking for some specific attributes. So there is a convenience module down here called set fluid source attributes, and it is passing in specific attributes for density, temperature, and velocity. And then you have a few additional attributes that are loosely hooked into the system that with a little bit of modification, you can start adding more detail, more information, I should say, into your simulation. So if I switch this guy back on, now you can get a feel for what the particles are doing by injecting all this data into your simulation. And I can start modifying it. For example, I can switch the temperature off. Now all we're getting is smoke. Conversely, I can do the same for density. And now all we're getting is fire. As I say, you can do, this is a fairly open mechanism. For example, as a quick demonstration, let me just switch off this guy for a minute. So what I can do is I can add an emitter based on, say, the fountain. Now, the one thing that you'll have to remember is at the moment, this is supported on GPU only. So I need to go in and just switch this to a GPU compute sim. And I'm going to just switch this guy off. I don't need the hits anymore. I'll just calm it down just a little bit so it stays within the bounds of the simulation. Open it up. So the only thing that I really want to copy across from here is this set fluid source attributes. So if I just Control C, and Control V it into the bottom. So now the attributes exist. And then when I switch on my fluid sim, in the emitter summary, there is a tab for the source. And instead of the particle source emitter, I'm now going to point it to my fountain. Now I'm sourcing data from a completely different emitter, and I can start playing around. Maybe I want to go completely crazy with the temperature. Now I'm getting the fluid sim to react to this different emitter. And then, if I switch this guy back on, I can go back onto my fluid sim, change the source back to source. And now we're going back here. It's quite a flexible framework, so feel free to have a play with it. On the emitter summary itself, grid controls, fairly standard stuff. You'll notice that this is where the links are made to the user parameters. So up here on the system node, you'll see that these are the things that exist on the component. And on the emitter summary, these are how they're actually influencing the emitter itself. So this is where the size of the domain is controlled and the resolution and all these different boundaries. At the moment, by default, everything is open, but I can start closing these off just by toggling this and let the emitter recompile. And then the fluid will start to react as though it's hitting more of a wall at the top of this domain. Okay. Simulation tab. This is where most of the key parameters that you'll want to adjust live. Collide against. This gives you an idea of the type of things that we can collide against, and each one is controlled independently just for performance reasons and also convenience. But you can start toggling these on and then hooking up depth maps and all the rest of those things. Under the simulation, anyone who's played around with fluids before, I think a lot of these parameters should be familiar. Vorticity confinement is really good for adding detail. Let me just switch off the display on my particle source. So vorticity confinement is basically amplifying turbulence at the resolution of the cells within the sim. So if I switch this to 0, you may notice that things start to look a little bit smoother. If I go back to 10, hopefully you'll see a bit more detail. But then, of course, we can go crazier. And even more crazy. At a certain point, it'll break. It's really fun.
Oh, no.
I know. So I would say vorticity confinement, very useful. Dial in your resolution that you think you're going to stick with. And then start playing around with the amount. Turbulence is always an interesting thing, vorticity confinement included, is you can obviously overdo it and then you start to override some of the simulation itself, which is not always great. Pressure relaxation is another advanced attribute which controls the behavior of the simulation. Play around with that one too. Pressure solve iterations is useful. It's a quality versus performance type switch. If you've got collisions interacting with your fluids, you may want to play around with increasing the pressure solve iterations, but it will make things run slower. Density dissipation. At the moment it's at 1. If I go to 10, you'll see that the smoke starts to or in this case, pretty much vanish. If I set it to 0, then the smoke will hang around for a lot longer. Similarly with the fire. So if I go up to 10, and we get a lot less fire, it's basically just going away a lot quicker. Velocity dissipation, you could kind of think of that as drag. It's going to do basically slow down your simulation. And then buoyancy controls, we have controls for density buoyancy and temperature buoyancy. The default is to have the temperature buoyancy on. If I set that to 0, it'll no longer rise towards the top of the domain. If I set it to 10, it'll go absolutely crazy. And then Density buoyancy is kind of the inverse of that. So whereas temperature buoyancy causes the simulation to rise, density buoyancy causes it to sink. So this is more of a kind of like a heavy dust kind of effect. Gravity is exposed. You can play with that if you wish. Let's see. So if I mess around with the gravity, and that is going to change the way that your simulation behaves. I don't often play with gravity, I must admit, but it is there for you to play with should you wish. Okay, let's move on to rendering. So there are several options for how you want to render this stuff. Controls that are exposed at the moment on for density is we're doing a linear ramp between the data that's in the grid and what you want to consider as zero opacity and full opacity. So this density range here, this is specifying what that range of data values is that you want to map. So I'm mapping a value of 0.1 that exists within the grid to full opacity, for want of a better term. So if I increase this, then you'll notice that the lookup into that data value is more of a larger range, and your smoke gets less opaque because of that. You also have the option of a much finer control by using a curve. It uses the same range, but instead of using just a linear ramp, you can start to play around with exactly the types of controls that you wish. So you can have a steeper ramp up into full opacity if you wish. And then, of course, you can switch it off completely and just get fire. Now, you'll notice that the fire at the moment, we're using a black body curve. Black body curve it's a fairly standard way of mapping temperature values to color values or frequencies. We do some multiplications under the hood, so we're not dealing with crazy values to get it into the appropriate range. The one thing to keep in mind here is we have a curve here, and this can be used to control the full color of the fire. Let me just switch it on. Whoa, crazy. So if you want to change the color of your fire, you can go in here and you can create all sorts of interesting effects. That gives you a much more direct control for strange behaviors or magic effects and stuff like that. Down here, you can control the opacity. This is the opacity of the fire component. So as I drag it to the right, I'm picking up less and less of the fire. I'm basically ramping it out at much higher temperatures so it disappears much quicker. This opacity curve is also taken into effect on the black body. So while black body is using colors from your traditional black body curve, the opacity is being controlled by here. So if you're starting to see black fringing, like if I drag this all the way over here, we're probably getting a little bit more black than I would like. If I drag this up here, then I can start to get rid of that black. And then when I switch back on my smoke, maybe it'll look a little bit more natural. Render step size mult is a quality switch. If I lower this, the ray marcher, as it goes through the volume, will take more steps, which will help resolve detail at the expense of making your render longer. The last thing to talk about under here is the lights. This is where the hook is to go to your scene lighting. And if you open up the advanced, you'll see what the default lighting is here. And you can modify that so that these are the different defaults that happens if the actor is not hooked up in your level to directional lights. Debug can be useful. Debug source is a simple one. So instead of accumulating data into the sim, this is replacing data in the sim. So this is a good thing to look at if you're like, I'm not getting anything out of my sim, I have no clue what is going on. Is my source completely broken? If you switch this on, it'll at least show you that data is making it into the simulation. And the reason why it is so dim here is because we typically add data into the simulation. So you get a lot more intense as it accumulates over multiple frames. And the other one is a debug slice. Now this is where your sources are working. Now you want to make sure that your simulation is actually doing something, even though your render may still be not giving you the correct results. So this is changing the renderer itself and just giving you a slice of the data. Red being density, green being temperature, and then the blue is the shadowing information that's going on here. And you can move this slice around or change it to a different axis just to make sure that you see the information that you care about. I'll briefly go over scalability. We've exposed several of the attributes as overrides, and this tab here is useful for cinematic use. So if anyone has used Movie Render Queue, there is a mode there called Game Overrides, and that allows you to set a higher scalability quality level when you're running Movie Render Queue compared to what you're using in engine. So I use this quite a lot. The default is that the quality setting is set to cinematic, which is what the Movie Render Queue will default to when it runs out of frames. So it's automatically going to make sure that your bounds are switched off, but it also means that you can override things like the resolution, which is a good one. So while you're in editor, you can be running at a much lower resolution. And then as soon as you hit Movie Render Queue, it'll pick up this override value, so you can put, a much larger value in here, something that doesn't have to be real time or something that your graphics card can handle. And then Movie Render Queue will work at that higher resolution. So that's quite useful for cinematics. Source, we've briefly covered this. This is what is controlling the data going into the simulation. You've got additional controls here. Scatter is just the term that we use for how we're putting particles into the grids. And you can switch it off here as well if you so wish. Just wait for it to recompile. So now I'm not getting the density contribution, therefore no smoke. Similar controls going on here. At the moment, we're using the radius, which is automatically hooked into the sprite scale attribute on the particles. If we don't use radius, we can just do it on the closest cell, for example, although in the case of velocity, the closest two cells. So different ways of controlling that as well. So those are all the main controls on the base template in this case. Please feel free to explore the other templates, play around with the fluids. They've deliberately been designed to be somewhat similar, especially with the gas 3D, but you'll also find similar kind of interactions with the fluids and the 2D gas. And we will be continuing to refine all these for future releases. So I don't know if Devon, if you're back with us, but
yeah, should be up and running now.
All right, then I'll hand over to Devon for the content examples hallway.
Cool. Thanks, Dan. That was great.
Yes, thank you so much for that. Especially, I have to say, changing the fire color was my favorite part.
It's very satisfying, I have to say.
It really is. Yeah.
Yeah.
All right. And now that we have put out the other fire, let's start up another one. Devin, if you would like to take it
How
on.
appropriate.
Sure. Hopefully this is working now after all that. So I did a deep dive, and now we're going to go into the more sort of general, just sort of show the breadth of the tool set side of things. So this is just the content hall, the Niagara Fluids content hall that ships with UE5. And so you can look at this at home on your own time and see everything that we're showing now. And really what we're going to focus on is the 4 different simulation types and, just the different things you can do with them. And an important thing to remember when we look through these is that, kind of like what Dan said, a lot of the same parameters are available for all the different simulations. So when you see something for 3D gas simulation, imagine that it can also be used for 3D liquid simulation, and there'll be some version of it for 2D simulations too. So let's just dive right in. The first thing being gas simulation, which Dan showed a bunch of already. This is sort of illustrating the difference between 2D and 3D simulation. So on the left, it's a 2D sim. You can see it has no depth to it. It's just on a plane. It's just oriented in world space. It's not oriented at the camera, which is something we can talk about later too. And on the right, we have one of the volume rendered fires, like what Dan showed. You can obviously go all the way in it. You can walk around it. You can see it from all the different angles. And obviously, there's a really big difference between these two as far as performance goes. 2D simulations are really fast. They use way less memory. And they're better for in-game sort of things and some cinematic shots. We've used it successfully on Fortnite trailer shots for really high resolution, like really detailed things. And the problem is that they can sometimes, if you're not really careful with how you craft them, they can look sort of flat and lack the sort of small scale detail that you would want to see in a fluid. And things tend to sort of glop together and you get like big rotating pieces of smoke and fire, as opposed to 3D simulations, which have really as much detail as you want. It sort of is more close to mimicking reality in that sense compared to 2D sims, with the downside being it uses way more memory and just is much slower than 2D sims. So these can be used for real-time or in-game uses, but in general, it's going to be something that needs to be very constrained and quite small potentially to get something that works well, and definitely only one at a time right now at least, unless you're very careful with how you craft them. So for example, in the ancient game demo that Epic had released, the fire inside of the robot's head was a 3D simulation that ran in real time along with all the other game elements, but that was a very small simulation enclosed in a very small space. So it's something to just keep in mind that 3D is more for cinematics and very specific real-time uses, whereas 2D can be much faster and used in lots of different scenarios. Okay, and we also support liquid simulations. So this uses a lot of the same code that the 3D gas simulation and the 2D gas simulation uses, except it's adapted to do liquid surfaces. So we kind of have the same trade-off here that we had before, and you can see the difference very easily here. So this 2D sim, again, is just on a plane. You have these 3D particles that, in this case at least, are only really moving in a plane, but the velocities of those particles are basically transferred to a grid. And then what happens is you solve the motion of the fluid based on those velocities from the particles, and then you transfer them back to the particles, and then you get some fluid motion. And we'll go into a little bit more about the actual simulation in a little bit. This is mainly just to illustrate the differences between the two. On the right, we have a just 3D liquid. And in this case, it's a very similar algorithm to the one on the left. And we have particles. You're seeing a surface, but there are particles here. And we'll get into what that means later. But it's rendered as a nice three-dimensional surface. So again, we have the exact same trade-off that we had before. The 2D liquids are much faster, can run under a millisecond, have all the advantages of things that you'd want to use in game. They exist in Fortnite, and so they're able to run in a game that needs to hit a very specific frame rate. They could be good when you have them camera facing, and we'll have an example of that in a little bit, where you can do things that sort of mimic a 3D shape, but are actually simulated in 2 dimensions. They're really not good for things like this type of fluid, where we're talking about this 2-dimensional, and we're just going to call it flip simulation, are not good for pools of water or rivers, but we'll show some other examples of simulators that are fast that do that kind of thing. And again, the 3D liquids, this is not much different than what we talked about with the gases. They're not very fast. They're really only good when you have a cinematic shot right now or a very specific real-time use. So we've released some footage out there where we do use it in real time, and you can have character interaction and things like that. It is possible, and it really needs to be the focus of your real-time experience or your game or whatever you're doing if you're going to use real-time 3D liquids. Because if you have lots of other stuff in the scene, if you have lots of geometry you're rendering, and you're using Lumen, it can get way too slow to really be working well in real time, because these fluids really will take any computation you can give it. These things can range from like running in real time to being something where you bake it out and it will take, half an hour or longer to simulate and render. Okay, so we're going to go into more specific uses. In this one, we have this explosion. Again, this is a 3D gas simulation, something similar to what Dan had talked about. And the really important thing that we're trying to show here is this sort of trade-off between quality and performance. A simulation like this, you really have two quantities that you're tracking. You have temperature and density. And Dan showed how you can remap the temperature to give you different colors, and you can like change the buoyancy to change how it rises, all these things. And what happens is these density values and temperature values are stored on a three-dimensional grid. So you can think of a 3D voxel grid as being just a 3D analog of a 2D image. So you have little cubes that represent the values, and they kind of move through that space defined by a bounding box. And the more of those cells that you have, the more detail it will give. So if you have far less cells, you'll get something really grainy that doesn't look very good. So we click on the little button, you can see it's just a super blocky simulation that really doesn't look nearly as good as it did before. And if we jump off of it, it looks much nicer. So the big difference here is that we're simulating far fewer cells. It runs way faster, but doesn't look as good. We back off from the button, it looks really nice, runs way slower. So there's a trade-off here, and a lot of fluid simulation work really depends on finding that right balance of what your resolution is for the amount of time you want to spend and the amount of memory you want to use. Okay. And next we'll show a fire. So Dan showed some stuff with fire, and he talked a little bit about the like render step size multiplier. And the interesting thing here is, so this is only using temperature, and there is no density. So this is only purely like a sort of, you can imagine a smokeless fire. And it's emitting from particles that are sort of placed on this knot surface. And what's really interesting about this one in particular is that sometimes you need to raise this render step size multiplier pretty high. And the reason is, when you do fire, you often want like really sharp details and sort of like things that break off of the fire as it rises. And in order to do that, a lot of times you need to remap the way you take temperature and turn it into a transmittance value. Or you can think about it just as opacity. So you sort of are isolating very specific bands of temperature. So like from between 0.1 and 0.9, you only get a positive non-zero transmittance there, but then everywhere else it's zero. So you can really isolate really fine detail. When you do this kind of thing, you can often need to reduce the step size significantly. So you need to adjust the render step size multiplier to accommodate that. Otherwise, you'll get like really grainy or striping sort of effects. But that's a more complicated sort of workflow, that we'll probably go into detail at some other point in the future when we do some demos on fire specifically. So another thing is the lighting. So we showed early on in the slides that you can light your fluids using lights in the scene. So for instance, this simulator is using 2 lights. And it's also, the other really neat thing it's doing is it's using this archway as a collider. So the smoke is emanating from below the arch, but then curving around it. And you can kind of see it really well from this perspective. And this is sort of the example of using a static mesh for collision and then using the mesh distance field associated with that static mesh. And it's a pretty robust system, and it can something that we actually kind of get quote unquote for free. If you have mesh distance fields enabled in your project, then you can really start to utilize them in the fluids without having to generate more data for collisions. So it's something definitely worth looking at if you're using mesh distance fields, because it can really add a lot of detail when you use them for colliders rather than only using basically bounding boxes or very simple shapes, which is sort of what it will default to if you don't have these. And another thing to keep in mind that we'll show in a little bit is that these mesh distance fields are usable with liquid simulations too. So it's something that's sort of generic in that sense. Here's a pretty fun example that's a little different. We have the ability to do colored smoke. So with colored smoke, it's a little different than what we were talking about before. Instead of only having a density value that's pushed around by the fluid velocity, you have a color. So in this case, we have a ring of particles with different color values that are emitting color into the fluid simulation, and the fluid is taking that color and swirling it along with whatever motion the fluid actually solves to have. And this is like a really nice technique that sometimes simulators don't support very well, and it can be kind of tricky to get the implementation right. But the advantage of doing this is that you can kind of do really interesting magical effects, or sort of more stylized things that utilize color in interesting ways, and get some really neat results with it. And if we click on this button, we see particles. And what to notice here is these aren't the source particles that are emitting into the fluid. These are particles that are just advecting along with the fluid. And so when we say particles are advecting, what we're really saying is that you have some particles in your simulation, and these are just Niagara particles, nothing fancy. You can sample the velocity of the fluid and then push them along with that velocity so it will move with it. And then you can also say, well, what's the color of the fluid at this point? And then you can sample the color, and then that particle will carry that color around. And for certain effects, doing particle advection can often be preferred over rendering the actual volume of the fluid. So it really depends on the types of things you want to do. All right, we're going to move on to 2D fluids, and specifically 2D gas simulations. And the first thing, when anyone talks about 2D simulation, you talk about it being camera facing or not. So here, look at the one on the left. Notice how it follows no matter where I am. It's always facing me, and it's just a camera facing sprite. And the simulation just rotates along and translates to follow the direction I'm looking. In general, if you're going to be placing something in a game, placing something in some live experience, you're going to want to use camera-facing 2D simulations. And the reason is that otherwise you're going to get something like on the right where it looks pretty good from one angle, but you go to the side and it just, you can see it looks like a plane immediately. So we have a toggle for this on the simulators. It's very easy to change to go from camera-facing to not camera-facing. And it's the kind of thing that you generally want to start. You want to start with it being camera-facing and work only in that mode. So it's, in general, you're going to be using camera-facing ones. You don't need to think as much about the non-camera-facing. So this is a pretty useful thing for games also, which is parented simulation. So in this case, we have this torch and a fire simulation that's just parented to it. And you can imagine if you just do this naively, you take a simulation, you parent it to the torch, and it's apparent, you could call it a quote unquote local space simulation. It'll just follow the torch and kind of just look like it does, even if it weren't parented. You won't get that motion associated with it. We have some templates and things like this that show how to do it where you can inherit the motion from the torch or from whatever you're parented from. And then also just be able to have the simulation move with the torch and sort of optimize so you can have like as small of a bounding box for that torch as possible, or sorry, the torch fire simulation. So it's not like you have it moving all over space and you have this enormous bounding box for the simulation that uses lots and lots of simulation cells. So you can really optimize to use as few simulation cells as possible that are just around the torch. And finally, with 2D simulations, we'll show using collision particles. So here we have some particles coming from the side in 3D, and we have this camera-facing smoke simulation. And you can see that the particles interact with the fluid. And notice on the right-hand side, right here, how it kind of pulls the fluid with it. That's because the velocity of these particles is imparted onto the fluid as it moves through it. And this is something you can get a lot of interesting detail. A lot of times when you do fluid simulation, whether it's 2D or 3D, a lot of the visual fidelity you get comes from modifying and building these sort of collisions. And the nice thing is with the 2D simulations is you have these different options to be able to have 3D particles interacting with a two-dimensional simulation that's camera aligned. And you can get some really neat effects with it. Cool. So we'll move on to something that's sort of, this is like a little more experimental and hasn't been used much in production, but is worthwhile to show just because it's something that sort of rounds out the tool set for 2D fluids. And so we're moving on to liquids now, and specifically 2D liquids. And what we're showing here is shallow water simulation. So this type of thing is when you have a plane of water and it only tracks the height of the fluid. So there's no volume to this. You can't have like big splashes with tendrils coming out like you would expect with like a 3D simulation. It is really just a height field. And we have a single particle moving through it. You know, you could have many, many particles. This is just for demonstration purposes, just the single one. And with this, you can, you know, do things like boat wakes. You can also have like raindrops with like rain particles falling into water. Really depends on what you want to do. There's a lot of flexibility with it. It's also very fast. So it's the kind of thing that doesn't really take a lot of computation. It can be the kind of thing that, you know, you can throw into a game and you can use. And it also pairs well with other types of 2D fluid simulation. So what we'll show next is a waterfall. And this is a 2D simulation that is camera facing, and it uses collisions with 3D objects. So this is using the global distance field that's generated in your Unreal scene if it's enabled. And it's the particles are colliding against it. And the fluid simulator is using it as a boundary. And the emitter is up here that's emitting in 3D. And then you get these nice sort of tendrils and chains of fluid purely from the 2D simulation. So what happens is these 3D particles are projected onto the camera-facing grid for the fluid simulation. And then you solve for some interesting fluid velocity and sample that back to the particles. And it holds up decently well when you kind of move and look at it from different perspectives. But this is a very cheap sim, and it's the kind of thing that if you can kind of work into some real-time environment, it can work really well. And it's definitely significantly faster than what we're going to show next, which is the 3D liquids. But it's a very flexible technique. And you could also do this with splashes. It works really well with splashes, where instead of having particles falling from the top, you can have an emitter of particles that sort of like shoots a blast of them, and then they all sort of like coalesce together, and it looks like a fluid in 3D, even though it's just solved in some 2D camera-facing plane. All right, and then the final thing we're going to show is all of the 3D liquids, and sort of go into a little more depth on it here so people can understand what's happening behind the scenes. So on this example, we have a couple interesting things happening. We have this cow that's kind of jumping up out of the fluid, and that motion is just controlled by sequencer, and it's a static mesh, and we're using the mesh distance field to get nice interaction with the fluid. And then we also have this statue, which is another static mesh, but it's non-moving, and it also uses just that mesh distance field that we've talked about. So, you know, these are the same kind of things you can use with gas simulations, although a lot of times liquid simulations depend much more on having really, really good collision models, because you want to have objects looking really accurate when they interact with the fluid. Because if they don't, if that cow were instead represented by a box, when you go up near it, and we just look at it real quick, it would look terrible, because you would just see a box just kind of, you know, being separated away from the water. And what we'll show also is if you click on the button, you can see the underlying particles. We mentioned that a long time ago that these liquid simulations are using an algorithm called FLIP, which simulates particles and will sort of track the velocity on the particles. And then in every time step, it'll put them into the grid. It'll solve to make sure that you have an incompressible fluid, something that has motion that you would expect from a fluid. And then it will sample it back to the particles. So the particles will actually update and move with the simulation. And you get a lot of nice energy out of the simulation. And this type of technique works really well. The one thing is, though, when you render the actual particles, it doesn't really look like a fluid surface. It looks cool. You can maybe use it for something stylized, but it doesn't actually look like a fluid surface. And what you need to do for that, and this will just toggle, so we're going to actually look at the fluid surface, is you take those particles and then you put them into a grid, and then you sort of imagine you can stretch a surface over that grid only where the particles are. And that will create a fluid surface that sort of represents where the particles are. And notice, this is not a perfect fluid surface by any means. It's very bumpy. It looks really jittery. This is sort of one of the areas that we're going to work on more in the future for real-time use. But for cinematic use, it's the kind of thing that's actually fairly easy to get rid of. It just requires more computation. So we have some examples where you can sort of use what Dan was talking about with the scalability settings to sort of only when you bake out the fluid render from Movie Render Queue, you can up the resolution of this fluid surface to be super high and smooth. So it really just matters with getting as many particles in there as you can and getting the resulting sign distance field, which is what you generate in order to build the surface, as high resolution as possible, and then smooth it a bunch. So you can get rid of these little pock marks and jittery areas. All right, one other thing that we support is collisions with skeletal meshes. And with that, you can have pools of water that your character walks through and like causes splashes or things like that. And it's a pretty flexible. It's a pretty flexible technique, as long as you don't require really, really detailed collisions, because what this uses is a hierarchy of implicit shapes that are parented to the skeletal mesh in order to drive the collisions really well. And in the future, we'll work on actually integrating more intricate collisions against an actual geometry. For example, one interesting thing that we did that we showed in the slides, where you have the Ancient One robot coming up out of water, those were actually all pieces of a static mesh colliding with the water, not these implicit shapes like boxes and cubes and things like that, or boxes and spheres and capsules. We had the actual static mesh pieces interacting with the water on the moving character. So this is something we can improve more in the future. And also note, obviously, this fluid surface is pretty ugly. A lot of these examples in here are really designed to run in real time. And obviously, it's all in one big hall. So, we're trying to keep things as light as possible so it can actually run without killing your computer. And the final example we're going to show in the hallway is a river. And there are a couple of interesting things here to note. The first being it's colliding, again, with another type of primitive that's just sort of native to Unreal, which is a landscape. So this landscape is just modeled like you would any other landscape in Unreal. And if we sort of place our fluid bounding box accurately and then add some emission, you can have the water sort of flow along with it. And the other thing to note here is look up there. You can see where the fluid is emitted from. So this is very different than the other examples we've shown with liquids, where in this case, all of the fluid is emitted from one specific point. It's not like we have a big pool of water and then you're having things splash in it. This has constant emission where you just have some particles that are emitted into the fluid with some velocity, and then they just sort of get advected through it. So this can be really nice for things like rivers. You can also use this type of 3D sim to do bespoke splashes rather than like having an object fall in the water and generate a splash. Just model some particles with some initial velocities and some shape, and then throw it into a simulator and you'll get something that looks like a splash. But also the last thing to show here is whitewater. And so what whitewater is basically these like white particles here, and it can help add a lot of detail. What it does is you take areas of high vorticity, so areas of the fluid that are churning a lot and rotating with like some interesting features, and you emit particles from those areas and then push them through the velocity field. And it can add a lot of surface detail, and you can start to see where the high velocity areas are. So as you can see this channel of the fluid, watch the whitewater particles above it, and then watch them sort of accelerate through that channel where it's narrower and there's higher pressure and higher velocity. It's the kind of system that we're going to be working on more in the future to add a lot more detail to the whitewater. But it can just add a lot of interesting stuff to your simulation. Cool, and that's it for this part of it. We have everything here. And I'll just exit out.
I'm going to have that scene set up in VR so I can just walk through it like an interactive museum.
That would be awesome.
Just one at a time. Oh, just, this really incredible smoke here, and now we have fire, and now there's water, and just a playground of fluid sim. That would be amazing.
That would be
It
really
is fun
great
to play with.
Yeah.
Yeah.
All right, I found our next agenda item, and it's that. But anyway, there are a ton of questions in chat.
Great.
If both of you are open to answering some of these, I'd love
Sure.
to dive into some of that.
Oh, absolutely. Ready for anything.
Awesome. Because there's some interesting ones in here, and I know you were saying that you're down for some hardball questions, so I'm gonna find a couple, see
All
if I
right.
can maybe trip you up a little bit on some of these.
Great. Thanks.
Well, I already got tripped up once with my computer, so how bad could it be?
No worries, no worries. So this one was interesting. A lot of these come with examples, so I'll also just give the examples that come with them because I feel like the context will probably make it a little bit easier to answer. And either of you are welcome to answer any of these questions. I'm not sure who would be better to answer any of them, so I'll just throw them out, and whoever wants it first can go for it. Do the fluids have collision handling such that you can flood a map and characters end up washed away?
So having characters washed away would require imparting the fluid velocities on other actors in the scene. That's something that we don't really support right now, but is really one of the next agenda items, is to be able to take fluid simulations and have what we're calling like two-way coupling. So you can have something where a fluid simulation can interact with some rigid body simulation, and then those rigid body sim pieces can like float in the water and things like that. It's the sort of thing you could hack together now a little bit. If you had particles that represent the things you want, the fluid can interact with particles in Niagara purely, but generally speaking in the engine, not right now, but we're on it.
Awesome. I love the idea of that. So good to know that that's a future plan. And also good to know that there are some little workarounds if that's something that people are interested in trying out as well. What would be the minimum requirements that you would recommend as far as a computer goes if people are interested in trying to start up with fluid simulation a little bit more, dive into it? What do you think would be at least a good starting place?
That's interesting. I haven't thought much about specifics for that. It's, honestly, like a lot of these can run on, I have a 3080 in here, and it works really great with these like really heavy simulations. I mean, we can do some pretty crazy stuff with it. That being said, it depends on what you want to do. So if you want to do 2D simulations, I would say pretty much any modern GPU, even on a laptop, should be fine. I don't know about specific numbers, but for 3D simulations, I think it'd be pretty tricky to work with something lower end. I don't know, Dan, what do you think? I haven't actually played with it much on lower end stuff recently.
It's one of those things. It's a quality versus performance trade-off on anything like this. So you could get it to run on a fairly low spec machine as long as all the settings are dialed way down, but then it's like, you're not going to get the kind of fidelity that you're probably wanting. Through the development cycle, I was using a 2080 without major issues. There comes a certain point, especially if you're trying to do very high-res simulations through Sequencer, where you don't care if it's running at 60 hertz or 30 hertz or whatever, that you just can't create a grid big enough if you don't have the memory in the card to support it. So there's always that trade-off.
Yeah, that's a good point, Dan. If you're doing 3D sims, as much GPU memory as possible is very helpful. For 2D sims, none of this really matters. You can work on a pretty low end thing. One thing to note that we'll plug here is no matter what GPU you have, always make sure your TDR is set really high, and we can provide some info on how to do that. It's sort of all over our docs and our tutorials already, but it's very important because otherwise, it will really not work very well. So it's one of these little things you have to just change in the registry. It's pretty easy.
Awesome. That's good to know. Make sure you're taking notes, everybody. There will be a pop quiz later. This next one is kind of aimed more so for beginners, but what would be your recommendation to start learning Fluid Sim and getting into it more, especially from a non-artist standpoint? Maybe somebody who isn't used to the more technical art side of things, but want to get into it.
Yeah, I mean, there's a ton of literature out there. There's some YouTube is full of tutorials as well. We have tutorials on the community hub now, which basically goes over the technicalities of this particular system. It is actually a good area that we will probably do a tutorial for ourselves in the future, to break it down, to give you even more of the fundamentals of getting going with this stuff. Yeah, I mean, personally, I learned at school and then at work, so just through experience. A lot of trial and error, a lot of just playing around with the settings and seeing what it does, and trying to figure out what the analogs are between the real world and how smoke and fire behaves in the real world, and then how we fake that in the computer. But really just play with it, and with time you get a feel for what the fluid is going to do, and it's fun to mess around with it as well, especially with this real-time application.
And Dan's tutorial, one of the early ones we have on the community hub, is really good for just kind of going over like the various parameters that you might want to change. And it's the kind of thing that you can like play back and like, sort of like rewind and look at, and it can be really helpful just sort of like learning how to affect fluids. Because I think what you said really makes sense, is that like the biggest problem with learning fluids is having intuition with the settings. And Unreal is a great place to learn this intuition because it's real time by nature. So you can get immediate feedback, whereas it can often be really hard if the simulation's slower to like gain the knowledge of like, oh, if I double vorticity confinement and reduce my gravity, what happens? Like, well, you don't want to. Sometimes you have to just wait a long time, but you can have like really quick feedback.
Really great tips. So a couple things that we learned from that is, one, just try it. Get in there and try it and do your best, see where it goes. And two, set fires so you know what fires actually look like.
I'm not promoting any of that. But yes.
You can always just go look at the ocean too, like liquids are really safe, or like
from a safe distance.
Yeah, like just go out in the rain and appreciate with the puddles. I don't know.
Yeah, that does sound maybe a little safer. That's probably the better way to go about it. All right, next up, any examples or tips and tricks that you might have for somebody who's trying to make a more stylized looking fluid?
Interesting.
Yes, I mean, stylized covers a multitude of looks. Playing around with the color of the fire is a great first step to give you that weird look. We don't have the hooks in the material right now to really kind of like do a cartoon shader or anything like that. That's definitely something that could be done. One other way that you can play around with it is the color of the fire, for example, is controlled by a ramp. Typically, it's a very smooth transition from color to color to color. You can get some kind of wacky results, very stylized results, by having a stepped curve from color to color. So you get a very hard transition from temperature values from, say, like blue to red to yellow. And it can look very trippy. And then as far as the motion is concerned, that's a difficult one because the whole point of this system is to give us realistic motion. And then to try and then strip that back, it's something that you would need to experiment with. There are definite things, deliberately lowering the resolution is a good way of doing it. Cranking up turbulence to crazy amounts will also do some interesting things. But at the end of the day, we're trying to do a realistic simulation here. So, your mileage may vary as to exactly what it is you're trying to art direct. But it's definitely something that you should experiment with and play with.
I think that's a really interesting way to look at it as well, is the point of it was to try and get as close to a realistic simulation as you can. So I almost feel like it would be easier to end up doing something more stylized after you learned how to make it realistic in the first place, because then you know where to push and pull to get something that still looks accurate but stylized.
Yeah, absolutely. Yeah. I suppose one other thing that just occurred to me as well is we have a system for advecting particles through a fluid. You can get some very stylized looks. For example, you can attach cubes to particles, render the cubes as they're advecting through the fluid. So it's going to look very bizarre with all these cubes that can be, you can scale them up according to the temperature or whatever. But you're basically got a cube which looks, a Minecraft fire, for want of a better term. So there's definitely some scope there as well to play with. I might actually try that. That sounds kind of fun.
Yeah, that sounds awesome. That's something we definitely haven't tried yet.
Yeah.
And I want to add homework for someone, which is it'd be awesome if someone implemented, more advanced user, potentially shape matching using the static mesh collisions that we have and like the mesh distance fields. There's a whole broad range of literature on this topic of like taking shapes represented by sign distance fields. So, it's a volume where at each point in the volume, it tells you how far you are from a surface. Taking that representation of geometry and then trying to get smoke to naturally fill or move along that geometry. So we have all of the pieces. The one little nugget that we don't have is that bit that like makes a force that like pushes it into that shape, and like maybe massages it in different ways, but like everything's there. So I want to hopefully see someone try to do that. That'd be really cool.
There we go. The challenge has been put forth. I need a time limit for this one. They need it into you by...
Oh, geez. Next year.
Yeah.
Okay, next year. That's generous, I would say. In a sort of similar vein, there was also, just speaking about using cubes for some of the fluid particles and all that, there was a question of what somebody would want to do if they wanted to mimic something that was a bit granular, like maybe sand, for example. Would they still be able to use these similar systems?
That's a great question. There are algorithms for modifying the type of liquid simulation that we're doing, Flip, to do granulars. That being said, I don't necessarily recommend that. I would say instead it's sort of like somewhat of an Easter egg with the Niagara fluids. There's a directory that says sand, and then there's a sand emitter and a sand system there. That implements something completely different for doing granulars, which is position-based dynamics, and it uses the neighbor grid, which is something that a lot of people out there have been using for various things that are similar to this. I'd recommend that being the first place that you do it, and it's a pure particle simulation. and the only thing you use a grid for is to be able to get neighboring particles. So I would experiment with the sand system in Niagara Fluids.
I know Flip has been used for sand on movies. It was used for sand in The Force Awakens, actually, by one company. It just does not have the same level of constraint from grain to grain that you would hope for. So it can be a cheat, a workaround, but it's not as accurate as using the position-based dynamic solution.
The downside of the position-based dynamics is that when you have big piles of sand and you expect it to like keep its volume, it can be really challenging to do that in real time because of the number of iterations of you're basically figuring out all of the particles that are stacked on top of one another. And when you have like a big pile, it'll generally just sort of like sag down to be smaller. So that can be a really big challenge with granulars, in particular with position-based dynamics.
Interesting, yeah. So it's a similar tool, but different in implementation.
Yeah, and it's something that
Awesome.
we will continue to look at as well. It's a very powerful tool, and it's definitely an area of research.
Yeah.
And for those who have used the hair system that's in Unreal, the hair system also under the hood uses Niagara and uses position-based dynamics. So there's sort of an area here where we have like some interesting ways that we can sort of start to mix things and like utilize stuff that's written for hair to do granulars potentially, or things like that.
Awesome. Very cool. There is another question here that is very, very serious, and I had to make sure that it was included. But they need to know what the cow did to deserve the treatment that it's had.
It's a willing
It was
participant.
falling through smoke.
Yeah. She's a bit
daredevil.
of an adrenaline junkie. Yeah.
Yeah, exactly.
Okay, so we can confidently say no digital cows were harmed in the creation of these simulations.
100%.
Perfect. Going back to our museum of fluids, by the way, is there a clever way that you use to loop those simulations? Because it seems like some people have tried to loop and it doesn't end up looking correct, or maybe there's a jitter between the start and end. So do you have any tips for making that loop a little more fluidly? No pun intended.
Yeah, I mean that's a very interesting topic. I would say looping live simulations is something I have not looked into. It hasn't come up in what I've done. There are definitely interesting ways you could start to do that. I think the more interesting thing to me when we talk about looping is more about when you start baking these things out. And this is sort of something that Dan, did you go over the baker when I was dealing with computer stuff?
I did not actually know. We could very quickly go over it now, I suppose.
It might be worth it. I mean,
that's the interest, yeah.
Yeah, I mean, I can give a little intro while you get it, if you want to get it set up a little, and then.
Yeah, I mean, I'm ready to go whenever I can.
You're ready? Okay, yeah. I'll just say that specifically looping fluids with the baker is kind of a neat thing you can do that we haven't done much of. But the idea would be that you have some sequence of fluid frames that you bake out into a flip book, or eventually as a volume texture, but we're not there yet. And then you have a way of sort of just looping that texture. So you sort of are blending the frames. So when you get to the end, you're actually blending towards the start frame. That's something that is actually really not very tricky to do. But actually, yeah, is a great point. I think we should really show the baker because this is something people are really going to like.
Yeah. Yeah, I should have done that. So the baker is a new tool. It's embedded within the Niagara editor in 5.0 right now. It should be on by default. If it's not, there is a project setting for it to switch it on, but I do believe it is the default to have it on right now. So this brings up this new panel. It's a new tool. I'm just going to pause the actual Niagara editor itself to save on performance. So it's giving us a live preview of what our sim looks like, and we can move it around. Consider this as kind of like the camera that you're going to bake this simulation into. There are controls further down here. It tells you this acts like a frames per second. You can think of it as in sequencer. If you're wanting your sequence to run at 30 frames per second, this is going to enforce that particular frame rate. So you can set that to 30, and it may mean that your simulation reacts slightly different because the delta time now matches what you expect. You can pick how many frames, how many seconds, I should say, that you want to bake. You can even have like a warm-up time. So if you don't want to see that first second, you can set your start seconds to 1, and it'll run it up, then start to record. Number of frames. If you think of your typical flipbook atlas type texture, this one is going to bake an 8x8 texture for you. And then if I open this up, sorry, it's a bit of a dive down into all these settings. So the texture size default is just 1K, and you can see that the resolution is pretty low on what it's showing right now. But if I 2K, for example, then for a sprite-based simulation that is going to be used, the result of this flipbook, maybe this is the resolution that is good enough for you for now. Various options on cameras that you can use, perspective and orthographic cameras. I do recommend sticking with the perspective camera for fluids. The material is not really supporting orthographic cameras right now, but you can get a similar kind of look by changing the field of view. At the moment it's set to a default of 90, but if you lower that to 10 or 20 and then just move your camera further out, you'll get something that looks more like an orthographic. And then there are a ton of things that you can bake out here. None is the default, and that just means you're going to bake the thing that you're usually going to want, which is the scene color plus an alpha. So I do recommend you just stick with none for now. But all of these different buffers, depending upon what you're baking, and remember, this is not just for fluids, this is for anything that you can visualize in your Niagara editor, so any particles or mesh particles or whatever it is that you want. So a lot of these things, you can, if your material supports it, you can bake them out into flipbooks, including any particle attributes that you may have. Your mileage will vary. You'll have to see whether your material is supporting it, and you may have to write your own material to do something meaningful with this data before you bake it out. But that is all there. And then finally, this is the location on the content in the content browser, should you wish, when you want to find it. Again, I recommend for the first run, leave it at none. The bake button is up here. So if I hit it, it's going to generate the texture, and then it's going to ask me where I want it in the content browser. So it's going to default to the location that matches where your simulation is, and it's going to try and call it something somewhat meaningful. If I hit save, now on the right-hand side, we can see this is the sprite representation of the fluid sim, and it's filled in this location here. So if I double-click this guy, this is the texture. You can find it in the same location in your content browser, and it's ready now to be placed onto a more traditional particle-based particle sim. Yeah, so that's really a very quick lowdown of the Baker. There is a tutorial on the community hub for the Baker as well. So yeah, I think this is going to be really useful for a lot of people. You can create different variations based off a fluid sim, so you're not constantly incurring the cost of a fluid sim in your games. These are ideal for background fires or explosions or smoke plumes, and it's all generated in the engine. You don't have to keep hopping in and out of other applications to do this stuff now. Yeah, so that's pretty much it. Can't hear you, Tina.
I think you might be muted, Tina.
All right. Everybody gets 10 seconds to roast me for that. ready, go. No. But what I was saying was that it was incredible. Also, chat was absolutely freaking out once they saw everything going on with the baker there. That was really, really incredible and
Great.
is kind of a game changer for a lot of things, it seems. So
It is, and it's being actively worked on now. Stu McKenna, the engineer who put this together, is fantastic. We're going to keep building it up and making it. We've already thinking about adding camera bookmarks to make variations easier to regenerate at a later date. Lots of development going to go into the baker as well.
And I've got to add that, the obvious question that probably popped up is like, when are we going to support volumes and baking out those instead of just a 2D flipbook? And that's actively in development too, because that will be the primary workflow that we'd envision people using this for when they're doing cinematic work, is that if you're using MRQ, eventually you'll have this workflow where you have your fluid shot, you bake out your fluid, and then you only read that in when you're rendering the full final frames. So it'll all be an engine. It'll just be easy, to generate these sort of caches.
that's awesome. I'm going to have to go in there and start playing around with Niagara myself, honestly.
Absolutely. Yeah, please do.
Yeah.
All right. For these next few questions, these are more of the ones that come with examples. If you're game for that, I thought they could be kind of fun.
Cool.
Yeah.
So, for example, somebody wants to make a water gun. Would you be able to use a fluid simulation as a projectile for something like that?
As a projectile that affects the world, I guess probably that's what they mean.
Maybe,
I mean, in that
yeah.
case, it's kind of similar to the question that we had before about flooding in a world and having it push things around. There are ways to hack it for now, but to have the water really correctly interact with things is tricky. Probably if it were me, what I would do in that situation is the hack would be you'd have your water cannon, you'd have water spewing out of it that looks like water. You'd also have a separate particle system that's a CPU based one that has similar velocity, so you kind of know roughly where the water is going. The correct way to do this that you can do now, which is a little more complicated, would be to do a readback. I can't remember what the interface is for that, but to get GPU particles back into the CPU in blueprints. And then once it's there, you're good. It'll be like 1 or 2 frames latent, but it works really well. And it's definitely doable. It's more just, is it like fully encapsulated in this like workflow for physics? No. Is it possible? Absolutely.
Yeah, the blueprint readback, there is an example of that in the Niagara Advanced hallway in the Content Examples project. It's really powerful. There are certain limitations, of course, because you're reading back from the GPU, so there's a limited number of particles that you want to do that with. But there's a ton of cool stuff in the Niagara and Niagara Advanced maps within the Content Examples. So yeah, check that out too. Just a little bit extra on that. We've already done an example with a flamethrower using the fluid system attached to a gun. I actually attached one to the Lyra character, and there is a little movie of that on the community hub. One of the fluid pages has just a very quick kind of string of shots just showing the type of things that we've experimented with, and the flamethrower works. But you need that parented sim technique that Devon talked about in the hallway with the torch moving backwards and forwards. You can do the same thing with the flamethrower, and you just parent the sim to the gun and use that instead. And it's effective. It's expensive, but it's really effective.
And that was a 3D sim too, right?
Yeah.
Yep.
Awesome. That sounds like the funnest day of work ever.
It was pretty cool. Yeah. Once I got it going, I'm like, wow, this is fun. Yeah.
Yeah, I can't imagine getting that email. Just, hey, Dan, we need you to make us a flamethrower.
Yeah, one of the joys of effects work. Yeah.
So how would LODs work for these simulations?
Yeah, that's a great question. Really good question. That is the kind of thing that right now is bespoke. It's the kind of thing that you would have to put together yourself. There are ways of, just thinking off the top of my head that you could start to throw this together. You could have a baked out version of a sim and you do some scalability. So at a distance, you switch over to the baked out version. You can do stuff where it goes from 3D to 2D in theory. All these are, you could set them up. There's no built-in system for them. Sort of our dream is to kind of be able to do this more automatically and have LODs and like variable resolution that kind of can work at different distances and like switch between these different types of sims. Big project, but it would be awesome to really nail that in the future. And that's really one of our goals.
And the technique would change based on the type of effect that you're trying to mimic as well. If you're doing an explosion where you've got a clearly defined start and end, and then the event is over, you can, in theory, have your hero sim, which is a full 3D sim. It's interacting with the ground, with the set, with characters. Then for the explosions that's happening in the mid-ground, then you have your baked sprite version or a 2D version even. And as you go further and further back, once you've gone into the realms of baking it out to an atlas, then you can obviously do the LODs semi-automatically with that. If you've got a standing fire and you want to be able to just walk away from a fire and step through LODs that way, that's a much bigger challenge, because as you transition, the dynamics are going to change. That is an area of research that we'll really be wanting to look into. Yeah.
And getting that blending correct is really hard for a 3D sim, or like for a live simulation, whether it's 3D or 2D.
Yeah, I imagine. It does sound like quite a challenge just to not have it pop crazily and be
As
really
soon as you change
obvious.
the resolution, the simulation changes completely. So
Yeah.
it's one of the challenges is to be able to, do a low res sim and get the rough dynamics running correctly, then go to a high res sim and then maintain the same gross motion. Often when you increase the resolution, you really have to redial all the data that's being pumped into the sim to compensate for it.
Yeah.
Yeah.
Man, I didn't think about how difficult that would be actually until now, but yeah,
It's a
that does sound
challenge.
like a huge challenge.
It's a sort of thing we can work. I think there's some minutia in the simulator that we can improve to get the results to be agnostic to resolution changes, but it is a challenging problem. I think we can do better at it for sure. But it's one of those things, if you're working on some big movie cinematic shot and it's like the last little bit and you want more detail, even if you have the perfect system for having to be agnostic to resolution changes, it's going to change your sim, because that's part of what you want more detail. So that's going to be a different sim.
Yeah, absolutely. Well, going to a slightly broader question. What are some general, both best practices and big no-nos you should avoid while playing and using these sims?
I mean,
The main ones that spring to mind are just be careful with resolution. It's that fine balance. You want as much resolution as you can possibly squeeze out of it. But that has, if you go too far, you can kill your machine. You can overload
not
the
permanently.
GPU. Not permanently, no. but for that particular session, it's like too much data. I can't handle it. I have to shut you down. And also, there's also considerations like Devon has said. It's like if the fluid is not the primary storytelling piece within your game or whatever it is that you're doing, then you have that negotiation of, I really need this amount of memory, or I really need this amount of milliseconds to run this fluid sim. You've got to just, constrain yourself to those things. I wouldn't say there's no particular no-nos involved here. It's all to do with how many resources do you have to play with, and then I encourage people to experiment and see what happens. Some of it will work, some of it won't, but that's half the fun. Yeah.
I would add that it's like a mild no-no, or to try to avoid, is when you have an emitter and you're using particles as a source, really try not to emit too many particles, because that can end up, the sourcing can end up being like the bottleneck of the sim. That's something that you really need to watch out for, and like really balancing the size of the particles and the number of particles that's appropriate for your simulation. And I would say with resolution, trying to go as high as you can, as early as you can, and have it still be in real time is always a good way to go. So you're not upping the resolution later. Like work at a high resolution to start out with, if you can.
One thing we've not talked about is determinism, which for cinematics use and visual effects is important. You know, if you run the sim on take one and you've not changed anything, then you want it to look exactly the same on takes 2, 3, 4, 5, until you actually do a deliberate change. That does require a little bit of forethought on how you prepare your particle sources, which obviously also needs to be deterministic. And then we have a cine template for the explosions, which uses a deterministic way of sourcing particles into the fluids. And that's something that you should prepare ahead of time. If you know that determinism is critical for your use case, then use one of the cine templates. And that is, again, another tutorial that I'll be putting up in the coming weeks as to how to set up determinism in any system, or copy it across, just to make sure that your simulation is repeatable.
Awesome. Yeah. And with all those tutorials and stuff, I know we've talked about the hub a couple times, so I'm going to put in a quick shameless plug in for our new community hub. That is dev.epicgames.com/community. If you go there, there's a ton of incredible stuff there, including all of the tutorials that they've talked about so far in this stream. So if you haven't gone over there and signed up and made an account so you can go through all that incredible content, I highly, highly recommend that you do. It's very helpful, I promise. All right, so next, this is about the containers, actually. Can the size of the container be dynamically resized based on the simulation of the fluid, or do you have to resize the container based on how big you need the simulation?
Yeah, right now, the best workflow is to you size the fluid based on what you want it to be. There's no dynamic resizing with the fluids. Eventually, we'll look into doing sparse simulations, which is kind of a way around this, where you can have the fluid kind of go anywhere and it will just work, and it'll expand and like only simulate where there's fluid going on. But right now, you kind of just set your fluid box up, and then make sure it encapsulates your fluid and adjust it as you need to.
Awesome. For your 3D sims that you were talking about, does the size of that matter when it comes to memory usage? Or is it just you make it and then it uses a set amount of memory, or does the actual size of it play into that as well?
The actual size of it doesn't really matter. It's really the number of cells that you use. So you could have a little tiny bit of smoke, coming up off of a candle, and you want that as high resolution as possible. And you say it's 512 by 512 by 512. You could also have a 512 by 512 by 512 cloud that lives in the world, and heck, an airplane goes through and it swirls around. Those would use the same amount of memory.
Okay.
But just to be clear, we're using uniform grids. We are filling the entire domain with cells. We are not doing anything to only generate cells where we currently need them within those bounds. I mean, this is echoing back again to the whole sparse grid development. So right now, it will fill. It'll reserve all the memory that it would need for that full domain. But you can change the actual scale of it with the resolution itself. Yeah.
And you definitely want to make sure when you're doing this that, like, for instance, a lot of times you need to look at the boundaries, and if you have smoke, you can start to see the smoke reach the boundary of the domain, and you get kind of a hard edge. So that means you either need to adjust your smoke or you need to make your bounding box bigger. So that's like one of the biggest gotchas, is like making sure that your fluid is fully contained inside of the grid and nothing ever touches the edges. Or if they do touch the edges, it's as subtle as possible.
Absolutely. So another example for you guys. If somebody wanted dynamic fly-through clouds, would they be able to be displaced in real time? Maybe if you're playing a Superman game, for example, and you fly through a cloud, would you be able to leave a hole where you flew through?
You could certainly set up the simulation to do that. It would probably be, if you're doing a 3D simulation, it would probably be pretty slow, but that's sort of the bread and butter of fluids, is having stuff kind of interact with it. So you could definitely do it, and it would look really cool. It just might use a lot of your GPU. You could probably hack some together with 2D simulations that approximates this, or other techniques. But if you wanted to do it with fluids, you certainly could.
Awesome. That one was one that I was personally very curious about because, like you said, I think it would be really cool. Just punch a bunch of holes through clouds, make a smiley face, and
Yeah, that would be really cool, actually. Yeah.
It's actually, there's one of the demo scenes that we have is in the editor, the simulation is running, and you can use a static mesh. And because you're in Simulate, you can grab, like what we were doing before, and you can start drawing things with the fluid, or drawing things in the fluid as well, just by using the collisions. And you have like a semi-static piece of volume in there. You can start messing about with it just by dragging collision volumes through it, and it will leave a trail and do all sorts of cool stuff with it, which is fun to play with. Yeah.
That sounds like fun.
Yeah.
Do you believe that real-time fluid simulation will be a big part of media in the next 10 to 20 years? Or do you think normal particles will stick around?
Both, basically. It depends on the application. I've been doing visual effects for a long time. As soon as grid simulations became viable, there was never any danger of them going away. They're immensely useful. You can set up quote unquote realistic simulations much easier than trying to fake it with just particles and analytic fields. So yes, I totally see 3D fluids, and fluids in general, especially as the hardware gets better and better. It's not going away. Equally, there are a ton of effects where gases are not appropriate. Projectiles, magical effects, all sorts of flocking behaviors. So I don't see particles going away either. We're just adding to the tool set, and just the scope of work that we can do in a realistic time frame just gets bigger. And as the hardware gets better, it'll get better and better.
Yeah, that's awesome. I like the idea of eventually us being able to have just a gigantic ocean and
Yeah,
fully simulated.
exactly. Yeah.
Yeah.
Welcome to the metaverse.
Yes. Speaking of the liquid simulation specifically for water, does it support math and physics in the sense of if you place mass into the water, will it raise by 1 centimeter or things like that? Or does it specifically just follow the simulation boundaries?
So I guess I'm not totally sure what it's asking. If you have collision objects and a collision object goes into the water, based on its volume, that amount of volume will be displaced, and the height of the container of liquid or whatever pool it's contained in will rise. Is it quote unquote physically correct as far as the units go? Absolutely not. It is definitely not. And that's just not realistic for these kind of things, especially in real time. As you kind of converge to the smallest number of cell size, the smallest cell size possible, and the most number of pressure iterations you can do, it can be more and more physically plausible or closer to what would be realistic. But there is amount of like a fudge factor in here because of just the intricacies and errors involved with the simulation.
Yeah.
And we've
So
had
it's
questions
as
come
close
up.
to realistic as you could get.
Yeah.
Well, it's
Good
one of
enough.
those things. Questions have come up about scientific visualization, and could this system be used in those applications? With the current implementation of the templates that we currently have, probably not. but it's such an open system that if you can do the math for it, then the framework is there for you to be able to implement it. And that's one of the great things about this system. It is open, and people can write any solver that they want to write within this framework.
Yeah. So the capability is definitely there. It is plausible. It's just not in the base package necessarily.
Exactly.
Yeah. And for the like for base visual effects, you don't really want to pay for that kind of accuracy sometimes. You're okay with it being off by a little bit to make it much faster, more flexible. That's kind of a trade-off between like scientific computation and visual effects. It's pretty common.
And entertainment, usually you want it more than reality anyway. It's always a case of, well, that's great, but now dial it up to 15. So yeah, at that point, physicality is a sliding scale.
Sure, yeah. That makes sense. For another example here that somebody came up with, is there, if you started a fire inside of a small room that had an opening in the roof, would there be a way to have the smoke specifically travel to that opening that goes out into open air?
So if you do that kind of thing, with the boundary conditions, if it knows all of the boundaries and there is that hole is in where the boundary mask is, then you will get smoke that goes up through it. If you want to art direct it in a non-physically based way, it kind of goes back to what we were talking about before, which is you can add force fields that kind of push it in that direction. But it will naturally kind of find the escape if that's one way to put it, I guess.
Absolutely. So it'll do it. Give it time and it'll find its way.
It'll find its way. Yep.
So for the smoke example that you had in the walkthrough, there's a couple questions about so that was just one simulation, right? That wasn't several colliding with each other. I think they're talking about the rainbow smoke specifically.
The rainbow smoke.
Yeah, that's just one simulation.
Yeah.
Yeah. And to have the fluids interact, they really need to exist within the same simulation so they can crosstalk, and it all happens.
The same system.
Yes.
Yeah, like Niagara system, like
right. So then they're not calculating as separate grid simulations. It is one simulation with the sourcing happening with multiple colors. If that made any kind of sense.
Yeah. It makes sense to me, and I barely know what I'm talking about, so. As another question from that lineup, they're wondering if the waterfall that was falling onto the rocks, if you moved the rocks, would it update where the water is falling lifetime?
Yeah, you could do that in the editor. Yeah, I mean the beauty of that is that it's just using these already predefined data structures that are in the engine as far as like how you track where objects are and things like that with the global distance field. So it kind of adheres to that kind of thing. So, it's kind of there are a lot of ways that you can kind of interact with the fluid in real time. Like I did a little demo where I made like a breaking wave, that, push water, then you watch the wave break and it looks kind of like a nice peeling wave with a barrel and all this stuff that, you kind of expect from watching some surfing footage. And like, I was working with the landscape and editing the landscape in real time, and then kind of just like restarting the simulation and seeing how the liquid simulation will respond to the landscape. So you can do these really, really cool editing workflows.
That sounds so much fun.
Yeah. I've spent a lot of time on that simulation.
I feel like this question kind of ties in a little bit with that, but they're wondering, since both of you have been working with Fluid Sim for a long time, it's something that both of you are obviously passionate about. What is the most difficult one that you have ever worked on?
I mean, personally, I guess I spent some time as an artist working on a movie a while ago, Puss in Boots, and it had this this tornado. You have this bean sprout coming up out of the ground, and there's this like tornado, and the camera starts from really far away and zooms in really close. So it was like you need to look good far away, then you need to look good really close up. That was really hard. So it was like multiple scales with a moving camera, and you couldn't use the same sim for all of the elements. So you had to do blending as the camera moved closer, and everything was art directed independently. To me, that was the hardest thing because it encapsulated all the things that I find hard about fluids. It's like it's moving camera near far, multiple layers, all pushed on top of one another, and it was very art directed. So
yeah, I would totally agree with all of that. It's especially if you're dealing with like a water surface, but you're in the boat, so you're right at the level of the water, and you wanting to get the high fidelity very close to camera, but you also have like a fleet of ships going off into the distance. You can't have the same cell size in world space close to camera as you would like 2 miles away. So you have to be like simulating multiple simulations all the way back to the horizon. And then it's like a data wrangling nightmare as you're trying to pass collisions backwards and forwards and interact a low res sim with a high res sim. And it's a lot of wrangling of data and simulations and getting them all chained together correctly. It's more of a logistical nightmare rather than an artistic nightmare before you even start. Yeah.
That sounds incredibly tedious.
Yeah.
All right. Well, that mostly encompasses the majority of questions that have come up. I'm sure that there are plenty more. If anybody does have further questions, please feel free to leave them on the forum post announcement for this stream, and we'll try and get back to you and answer some of those. But with that, for both of you, I will open the floor to the two of you. Do you have any final statements, closing statements for the people watching?
Please give it a go. Just have fun with it and let us know how you get on. It's in active development. We're very excited to have it released out there into the world, and we'd love to see what people can produce with it. Yeah.
Yeah, I just want to echo that too. I mean, please reach out. I think my Twitter handle's on here. You can send me a message. I'd love to interact with people and like see what they think and see what they needs improvement. Honestly, I just like am very open to feedback and like want to work with people on this, and just really excited to see what people can build with it.
Absolutely. Please post all of your cool stuff and tag us as well so we can see all the cool things that you've done as well. And
Yeah,
don't
please
forget, Devin put in that challenge, so I'm just saying.
Yep.
Get on
Just
it.
some shape matching smoke. Yeah.
But with that, thank you both so much for coming on today and speaking with all of us about just this incredible work that you've done and shown us these. Again, I really want that hallway as a VR walkthrough project because it would just be so much fun. It would be so incredible.
Yeah.
That'd be
There were
awesome, yeah.
so many tips and tricks and just incredible bits of information that you gave us. So I cannot thank you enough for taking the time to come and speak about it and share it with us.
Thanks for having us. It was a blast. I really enjoyed it.
Yeah. Thank you so much. This was a really wonderful thing to do.
Absolutely. And obviously, it seems like there is so much information compacted into these tools. So I'll just have to drag you back on for another stream.
All right. Sounds good.
Yeah, sounds good. Yeah.
I got the verbal agreement. So here we go. But of course, also, thank you everybody who came and watched as well. I really appreciate you being here and you interacting and asking questions. The show would not be what it is without you. So also, thank you for being here. Make sure you come in next week as well. We still are on our UE5 binge streak of content. So make sure you come in next week as well. Speaking of which, if you haven't already, please go download Unreal Engine 5 and experiment with all of the new tools. And specifically, go play around with this fluid sim and give it a go. Tell us how it all goes. And as well, make sure you go visit our hub so you can give us feedback on both the site and the engine itself. Don't forget to keep up with us at Unreal Engine on all social media, as well as come say hi in our forums where you can get the latest news and also find all links associated with today's stream, including the tutorials and where you can find some more information about the stuff that we talked about. But with that, thank you everybody so much for coming, and I'll see you next time.